Okay, so today we will finish up our lecture 4 on errors by looking at the examples. So I will work through a couple of examples of how to compute an error, of specifically truncation errors. And then we will actually have a couple of exercises prepared that are more like a practice for tests. So we will go back to practice for loops. And I've posted a slightly updated PowerPoint on Canvas if you want slides that have exercises in them. Okay, so let's go to the slide. Okay. So let's just laptop. Oh, maybe I should connect the laptop. That would be nice. But why isn't it showing anything? Oh, no, never mind. Okay. Can Rahul, can you go to my office? There should be those two connectors so you can get connected to Mac laptops to PGE on my desk, on the round desk. I will disconnect the other one. In the meantime, laptop. All right. Okay. So, just to remind you, we were mentioning round-off errors and truncation errors. So for round-off errors, we went through the whole review of how to actually represent numbers on a computer. And we know that we sort of have finite space to represent numbers, which can result in round-off errors for those numbers. Now I can have another source of error, and that is actually when I'm approximating formula mathematical expressions, that especially those that have infinite number of parts of a sum. For instance, I know that if I'm computing e to the x, the formula, the series, is actually 1 plus x squared over 2 factorial and so forth. And basically, depending on where I actually chop off this sum, and I have to do it somewhere, maybe at 1,000, maybe at 10,000, depending how much accuracy I'd like, I will introduce an error because there is a portion of this number that is not going to be there. So those are called truncation errors. Similar errors we will have in any kind of approximations. For instance, for derivatives, we're using something that is called finite differences. So you know already this is essentially a slope to the graph at this function that is going through 2 points. So basically this will approach as my difference between these points xi and xi plus 1 becomes smaller. This is actually going to approach the true derivative, but it's never precisely equal to the true derivative. So I always have a little bit of an error in there introduced by the formula. And that is also a sort of a truncation error because it's from the approximation thing. All right, so now we will just remind ourselves one of the most useful series in calculus is Taylor series, which says that, okay, if I know a value of a function at a point x0 as well as its derivatives, however many it is that I know at that point x0, then I can evaluate this function f of x for some x in the neighborhood of x0 using this formula. So I start with the value f of x0, and then I add difference x minus x0 times the derivative, first order derivative at x0, and 1 over 2 factorial square of the difference times the second derivative, and I can keep going, okay? As many derivatives as I know. So I basically have some sort of like a polynomial and an error sum here, because I have to chop this off somewhere. Okay? So essentially I start with this initial polynomial, which is nth order polynomial in x, that is my approximation. And whatever I chopped off, there is a theorem that you possibly remember, possibly don't remember from calculus, that says that this whatever is left over here, that is actual difference between this Pn of x and actual value f of x, actually has a form of x minus x0 to the n plus 1 divided by n plus 1 factorial times a derivative n plus 1 or the derivative of it. At some point, zeta here is denoted as zeta that is between x0 and x. Okay? So there is such a point that basically, so I know that my order of my values to the n plus 1, and why is this useful? If I'm actually really close to x0, this is a relatively small number, okay? Because I just raised something that is small to the n plus 1. So this difference, no matter how, well, and hopefully this derivative is limited in size as well. So basically this is a relatively small number, and I have a pretty good approximation with Pn. Yes?
So just a question, so obviously we can choose values for x naught, but can we choose a value for e, or
For E, this is zeta.
zeta?
Uh-huh.
How would you go about plugging
All
in
the
zeta?
theorem, you don't plug it in.
You don't
All
plug
the theorem says is that there exists such a zeta.
Okay.
But what you do in this case is that hopefully on this interval, you can actually find the limits on this. This is a function. This derivative is a function, okay? And it's a function on the interval x0 and x. So hopefully on that interval, you can find a way to limit it.
Okay.
So function f of x is equal to x. Obviously, it's limited by values x0 and x on that interval, right? So you know what possibly the minimum and maximum of the function are on that interval.
So zeta is just somewhere within that, and that's all we know.
Right,
We can't
that's all you
pinpoint.
know, you can't pick the value.
So when we talk about taking derivatives in the f of x minus h and f of x,
Mhm.
MATLAB plots points. So does that mean that we have to manually input the step in between each points, or will it connect those points and
It's gonna
extrapolate?
connect them, but it's an interpolation in the sense that it's just gonna put a straight segment in between points.
So that
That's just plotting.
when we make our set of points to plot, then do we have to include a really small step in between each so that we
Yes,
can make
so then it's gonna look continuous, but it's not really continuous, it's plotting points and interpolating in between.
How would we do that?
Huh?
How would we
You just define a very small step. You know how to, between x0 and x1, let's say that you're plotting something between x0 and x1, you know how to create with lin space a number of points in between. So you just choose a lot of points. How is that related to Taylor series?
it was on the previous slide.
Oh, okay. Okay. I was like, wait a second, did I mention plotting somewhere? Yes, so you would just plot. So basically that's also here, again, the same point. The closer I am here, the better approximation I will have. All right, so let's actually do, and just before that, so whenever I have some sort of iteration, so I'm going from one approximation, then I have a formula that tells me how to do next approximation based on the previous one, and so forth. Then I'm actually iterating. It's called iteration. And most of numerical techniques are set up so that you're iterating to get a solution. And in this iteration, you would like to iterate until you are accurate enough. And this accurate enough says, okay, I have some tolerance delta, and I'm hoping that my current iteration is close to the actual solution, meaning that the absolute value between the two is less than delta. Unfortunately, actual solution, you don't always know, you're looking for it, right? So you can't really tell. That's where Taylor series actually can give you bounds on your solution, so it's useful. In practice, what you will do, you will start iterating, and at some point you will see that these the two iterations that are next to each other are getting close. They're getting really similar. Okay? So the difference between the two iterations is getting very small. That's what practically we often can do when we are looking for solution. And this is going to make a little more sense once we actually start doing root finding. So in review, errors are unavoidable. Some of them that are avoidable we weed out by debugging, right? Those are our own typos and errors in the setup of the algorithm. But there are errors that cannot be avoided. One of them is round-off errors. Numbers to the right of a certain digit, depending on my accuracy, are discarded. Okay? And those can pile up if I do a lot of computation. And another one is truncation error, where I have a mathematical formula, for instance, series that is approximate, that I have to approximate. That means that I have to at some point chop off the number of elements that I'm counting. So let's actually do an exercise. Let's say that I have a function f of x. If you have a piece of paper, now would be a great time to pull it out. So there's a f of x is 1 over x plus 1. And I'm looking to do solution close to x0 is 1 using Taylor series. So then try to evaluate f of 3 and f of 2 using Taylor series approximation and using 1, 2, or 3 terms in that approximation. And at least for one of those, please compute relative and absolute error. And while you're doing that, while you're trying to do it yourself, I'm gonna do a setup here. So f of x is 1 over x plus 1, x0 is 1, and I'm interested in f of 2 and f of 3. Just gonna write the formula. You're probably getting a head start yourself, but I just wrote down things that I need. What I need to compute this, I need f prime of x0, I need f double prime of x0. So my f prime and f double prime are minus 1 over 1 plus x squared and 2 over 1 plus x cubed. So that means that f prime of 1 is minus 1 divided by 4, right? And if double prime of 1 is 2 over 8, which is 1 over 4. So now what are my approximations for f of 2? Basically, I put x is equal to 2 into the formula. So it's f of 1 plus 2 minus 1 f prime of 1, which is minus 1 over 4, plus, what is 2 factorial? What is 2 factorial? 2. So n factorial is 1 times 2 times 3 all the way to times n, right? So it's 1 over 2, 2 minus 1 squared, f prime of 2, f double prime of 1, which is 1 over 4. Okay. So now my first order approximation is, or zeroth order rather, if I just keep only one term. So this is zeroth order approximation, keeps only one term from Taylor series. That would be 1/2, which is f of x0. Okay? So f of 2 is approximately 0.5. Then my first order basically keeps two terms. So f of 2 is approximately 1/2 plus this. So I have two terms. So then I have minus, so it's 1/2 minus 1 over 4, right? It's 1 over 4, which is 0.25. And my second order keeps one more term. So my f of 2 is approximately 0.25. This is 1 plus 1 over 8. 1 over 8 is 125,375, right? Please watch it, I'm correct. So what is my actual solution? F of 2, well, it's simply 1 over 1 plus 2. Nobody's saying anything. So it's 1 over 3, which is 3, 3, 3, 3, and so forth. So I started my first or zeroth order approximation was just f of x0, which is 0.5. Then I went to 0.25, then 0.375. My next order would probably be a little less than this, and I would actually end up, if I kept more terms, I would get closer and closer, okay, in this order of approximations. Now what would be the absolute value, absolute error for this second order approximation? So my error absolute is basically my approximation minus actual value. So it's 375 minus 333. I'm going to keep 3 digits here. And what is my relative error? This divided by the actual value. Can somebody divide that for me? And I can, if I want to express that in percent, I can. Can somebody do that calculation?
It's like 0.121.
0.126%?
Yeah, it would be 12.6%.
So that's a little too small for percent. So as I keep more and more terms in this Taylor series, I'm going to get more accurate, so my relative error, both relative and absolute error, will go down. Okay. That's where my formula actually converges. Let's try the same exercise for f of 3. 3 is fairly far away from 1. And my Taylor series is actually guaranteed by theory to converge only on a small neighborhood. Small can be relative and it depends on a function, but it's on a small neighborhood around my x0. So let's try f of 3. You go try yourself and tell me what you get. Is Carson Young here? Carson Young? Dallas, you? So Dallas, what is the 0th order approximation if I keep only one term in Taylor series? Yeah, it's no. It's f of 1, right? And that's 1/2. Okay. So then the next one, you told me the next one probably, which is f of 1 plus 3 minus 1 times f prime of 1. Right? So it's 1/2 plus 2 times, what was f prime of 1? Can you remind me? F prime of x was minus 1 over 1 plus x squared, right?
Yeah.
So what is this? One half minus 1/2. 0. That's fine. So that's my second approximation. So this is what would be first order. I kept only terms, 2 terms. And my next one, let me ask somebody else. Which one? Oh. So what would be if I added the third term? It would be this plus the third term would be 3 minus 1 squared times f double prime of 1. This I know it's a 0. Can you quickly, what was f double prime of 1? What is f double prime of 1? So I don't have to go to my previous sheet. 1/4. So this would be 1/2 again, right? Actually, if I keep going, I'm gonna keep oscillating like this, and I'm not gonna get close to the true solution. What is the true solution? So in this case, I'm actually, so this is actual. If I decide to go with one more term, it's going to actually keep going back and forth. Yes?
I have a question. When you put like f of 3, does that mean that's like the third to the third degree of table 3, or does it mean you plug in 3 for x?
So all of these first three, are approximations. So I'm plugging in 3 for x.
Oh.
And I'm still using x0 as 1. So the way Taylor series works is that you're computing at the neighborhood of a point x0. And x is from that neighborhood.
So for like f is 1, that shouldn't it be like 1 plus 3 squared?
This one?
No, like the top right. Like it should be 4 squared. Shouldn't it be 1 plus x is x3?
Yeah, this is just a formula.
So what do you substitute in for x then?
These primes are always at x0.
Oh, okay.
Okay? That's how Taylor series works. Sorry, I just wrote down the formulas and this is the derivative.
Oh, okay. I was plugging in 3, so I got it.
Yeah. So all of these are always, let me actually, this calculated at x0 always, which is 1 in our case. Any other questions? So in this case, we are not converging, okay? So Taylor series doesn't give you a good solution. You can still go and find the approximation, it's just not a good one. So convergence is not always given. All right. Our other assignment here, if I actually go to the PowerPoint, was how accurate is approximation for the derivative at x0 is equal to 1 using x1 is 1.01. And in this case, I'm using formula for derivative, which is the following one. So my df of x calculated at xi, here I'm looking for the derivative at x0. So I is some sort of counter, 0, 1, 2, 3, 4. Okay. Is delta f over delta x, where delta f is sort of difference in the value of function evaluated at two neighboring points divided by the difference between those 2 points. So this is so-called a forward formula, forward finite difference. So let me go back to, yeah. So my df dx at x, I'm going to write it in terms of x0, is approximately f of x1 minus f of x0 divided by x1 minus x0. So if x0 is 1 and x1 is 101, okay, f of x1 is 1 over 1 plus 101 minus 1 over 2 divided by 1.01 minus 1. Can somebody quickly calculate what this is? Entire result. -0.24. Give me two more. 87. Okay. So what is my relative error in this case? The absolute error is the difference between the two, which is here in the third and fourth significant digits. And the relative value would be difference between the two divided by 0.25. Can Mark Ruckus? Mark here? Mark, can you compute that for me quickly? And let's do times 100%. Pretty accurate, yeah? Now, if I want to go even more accurate, typically in these formulas, I'm going to get closer to 1. So I could actually go and evaluate this for 1.001. So I'm going to leave that to you and to actually see that you're getting closer. So if x1 is 1.001, so I'm closer to x0, we're going to get more accurate. And you can quickly compute that for yourself. Okay? All right. Let me see what was the next assignment. My next exercise in this practice is what is the representation of 0.75 in base 10 in base 2? So we discussed at length when I actually have whole integer numbers. But I want you to think a little about this number as well. Mitchell Steinman? Did you get anywhere? You have no idea. All right. So what do we typically do? Let's say that let's say that I had 75. What would I do?
Let's see. We'd see how many like 2 to the whatever goes in it.
Mm-hmm. So let's actually give ourselves a 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. Then I have 8, 16, 32, 64, right? And then the next one would be larger. It'll be 128. So it's 64 plus what's left. What is left?
And 8.
And then I have 8.
And all this one.
Okay? So these are my powers of 2, right? And then basically I would say, this is 2, 3, 4, 5, 6, right? This is 2 to the 6 plus 2 to the 3 plus 2 to the 1, or 0, correct? So then I would basically 1, 2, 3, 4, 5, 6. So I have 1 times 2 to the 0 plus 0 times 2 to the 1 plus 0 times 2 to the 2 plus 1 times 2 to the 3 plus 0 times 2 to the 4, 0, 1. Yeah? So this would be my base 2 representation. Yes?
That only adds up to 73.
Hmm?
This only adds up to 73.
Uh-oh. So did we miss a 2?
Yeah, we missed it.
Okay. There you go. Correction made. Yeah? So now, well, I can behave the same for these point something, because if I think about decimal system, this is 7 times 0.1 plus 5 times 0.01. Am I correct? 0.75 in decimal system. Yes? So 0.75 in decimal system is 7 times 0.1 plus 5 times 0.01. Well, this is 10 to the minus 1. This is 10 to the minus 2. I'm still working in powers of 10. Yes? Now, what are my powers of 2? 2 to the minus 1 is what?
2 to the minus 1 is
0.5. 1 over 2, right? And 2 to the minus 2 is?
0.25.
Okay. So when I see my 0.75, what is the largest of these that I can fit in?
Oh, the 2 to the negative 1.
And then I have what left?
The 2 to the negative 2.
So it's 2 to the negative 1 plus 2 to the negative 2.
Okay.
So this in base 10 would be actually, so now I'm just going to put myself a point. It's going to be 0.11. Same system. Clear?
One, does the 0 in front make it negative?
No, this is just a number.
So leading 0 is
This is not the representation in computer just yet.
okay.
Okay?
And can you show us how you do it if you did 7.5 times 10 to the
This is
negative
this is conversion to base 2. Not representation in memory. This was just a little tricky to remind you of what the regular. So now if I added the 2, I would have this dot 11. So my 75.75 is this 1.11 in base 2. This is just conversion to base 2. This will get you a little. So we kind of take decimal system for granted without really thinking that it's 0.75 is 7 times the power of 10 times 5 times another power of 10. Okay? All right. Let's now move on to some programming assignments. I would still, so 0.01 I would still go, so then I would probably have to go to 2 to the minus 4 and work with that. And doesn't necessarily have, also it doesn't necessarily have exact representation, right? So it doesn't have to be exactly represented, which can be a problem. So let's actually start. We're going to start and we're going to continue this practice on Friday. So write the function sum squared of n that takes vector x as an input and returns the following sum. Sum of I is equal to, and n is size of vector x, x of I squared. And as you can see, we have like 4 practice questions here. So start working on this one. You have 5 minutes left. You can get ahead. So if you don't have a computer in front of you, start on a piece of paper. If you have a computer in front of you, then open up MATLAB. On the test, you will be required to write it on a piece of paper without a computer. So computer is great to check on you while you're practicing, but then you have to be comfortable enough to just write it on a piece of paper. So I asked for a function, and MATLAB is so very kind to remind me how a function looks like. Okay. So Valerie, if I have a function and I'm asking for x to be input and for that sum of squares to be output, what do you choose to make this first line as?
The function line?
Mm-hmm.
Function sum equals sum squared.
Mm-hmm.
And then the input as x.
Is x. Okay. So this is the first thing that you can write on the test for sure, even if you don't understand the rest of the problem. Okay, and that's going to get you some points. Now my x that is coming in is, we know that the good practice, and MATLAB is actually warning me that sum is actually a name, a function of a function. So I'm actually going to put some x just to avoid, there's a function called sum. And right now it's not set because of, well, I haven't started computing yet. So first thing, I have to do a sum of all x of I for all of the elements of my x. Okay. So first I have to know how many elements of x do I have. So how will I find out? Gianfranco? No, here. Michael Chen? So Michael, how will I find how many elements do I have in x? Length. Mm-hmm. Okay. And then I want to add up all of the elements. So what's a natural thing to use? For loop. Okay. So my for loop will be set to go from where to where? Okay. So now I have my shell of the for loop. And inside the for loop, I'm going to grab element x of I, square it, and do what? This sum x. So basically I'm gonna have sum x is equal to sum x plus x of I square. Yes? Oops, not x of 6, x of I. This would be a bug if I ever left it as 6. And then I would spend some time figuring out what do I have there. Am I done with this? Is this correct? Am I done? Yes. So I have to start from something. Computer doesn't know what to start from. And in terms of sums, I'm going to start from a 0. I'm going to save this. Sum squared. This is using a for loop to solve the problem. Yes.
You have to set it equal to 0 because it's not sure what data type it is if you don't set it to something.
If I just set it as 0, it's gonna work with everything in double, and there will be no problem. Okay.
If you didn't have that model, it
It would return an error because it didn't know what to start from. Like when it comes to the m for I is equal to 1, the sum x is equal to sum x, but what is sum x? And the problem will return. Yeah, you can try out whatever. Alright, yes?
Could we use the cumulative sum function for that? Or
No.
just write it?
So the whole point of this is that you cannot use the function sum. Okay.
How would we instantiate the sum as equaling 0 with the correct length?
Correct length.
Like if we know that it's going to have 6 terms in it, or that it has to add up.
Oh, no, this sum is the total sum.
X of I.
You have to know, so this is, n is going to be the length of x when I come in. That's it? That's the correct
Oh,
length.
okay, yeah, that's
Okay.
I was thinking of something else. What if we wanted to set something equal to 0, but have, 6 be a 1 by 6 array?
Oh, well, then you would define that array. Let's say that you're computing some 6 weird sums, okay? You would get your sum x as zeros of size 1/6.
Okay.
You would set 6 of them, and then you would compute them.
That makes sense. Thank
Mhm.
you.
Uh-huh.
So the ends convert them to mass, right? And then the mass will cancel out.
Hello.
The units will cancel out.